So who can tell us what this angle here is? This one, the one I have circled. What angle is that? So let's just call it theta or phi or whatever. Who can tell us what it is? There are three angles there. We want, from what we have discussed so far, we want to identify these three angles. So who can help us do that? So the first one, what is it?
Will it be
So, let's just say it is called phi. So if it is phi, what angle is it? Let's define those various angles.
the friction angle?
Is it a question?
I'm saying the angle of friction.
The angle of friction, that is the internal angle of friction. Exactly. Again, what angle is this? Someone else to tell us what it is. You need to identify them. In an objective test, you may have these diagrams and they will be denoted as 1, 2, psi 1, psi 2, psi 3. And a typical question might be, which of these diagrams may result in a planar failure? So you need to identify them. So which of these is this? These angles, what is it? We said this is internal angle of friction, which is a feature of the material itself from our Mohr circle. And you remember when I drew the Mohr circle, I told you that that line we have drawn, if anything exceeds it, if any stress exceeds that line, there's going to be a failure. And indeed, that is why some of the various conditions that permit plane failure to occur was talking about these various angles. So which of them is this one? Someone should tell us.
So that is the angle for the shear stress.
The angle for
the shear stress.
Shear stress. No, if you say that, I don't get it. Can you come again?
Okay, the angle we need to prevent the wall from sliding or failing. That will tell the slope of which the wall is currently tilted to.
Okay, so is anyone helping Mr. Kwe? Mr. Kwe, can you just look there and mention a name among the participants and let the person help you? Just call a friend. Okay, we have talked about the various angles that must be satisfied in order for a failure to occur, or that type of failure that will occur on a slope. We can say it is a planar. So assuming you are a geotechnical person, you had your angle of internal friction, which you established from your triaxial test in the laboratory. So you know that already. Then you also have already designed per your mine planning and design, depending on those internal angle of frictions and other material properties you established. Your mine design proved that your pitch slope, okay, should be this, which is what we call the phase, slope phase. This is the slope, and that is the angle of that slope is this one, and we denoted it as SF. That's the slope phase. slope face angle. Then this one is the angle of internal friction, which you have done from your triaxial test. Then you went to the field and realized that there has been a failure on your slope face. Then you decided to measure that angle that caused the failure. This was the line that caused the failure on your slope. Then you decide to measure that angle, which is this. You measured and you got a certain angle that is falling between your angle of internal friction and your design slope face angle. And that angle here, which is psi p, is the plane angle which caused the failure. So these are the various three conditions that must be satisfied in terms of the angles for a planar failure to occur. And we said that for us to avoid this type of failure, one of the things we needed to have done was for us to reduce this angle. So assuming this one, who can tell us, let's say this is 60. This one was 30. And assuming this is 45 or even 50. So it means that for this type of failure, if we were to avoid the planar failure here, then our angle should have been somewhere 55. Sorry, we should have an angle of 45 or 49. That could have helped us to avoid this type of failure. So it means that if our designed angle was here, failure wouldn't have occurred. So you have your slope face angle, your plane failure angle, and then your angle of internal friction. Those are the various things that can be satisfied for you to have. So planar failure analysis. So the slope geometries and groundwater conditions considered in this analysis are that slopes having a tension crack in the upper surface. Two geometries must be considered. So there should either be a tension crack in the upper surface of your slope and the slope with a tension crack in the face. These are the two things that occur for you to know that this type of failure is a planar failure, and so you can go on with your analysis. And then when the upper surface is horizontal, then you have your phi s being 0, and then you have the transition from one condition to the another occurs when the tension crack coincides with the slope crest. So I have this as my slope. Let me draw it here. So if I want to tell what from introduction to mining, this is the crest of this slope face, and that is the toe of the face. So it is saying that when the upper surface of the horizontal, okay, so it's just like the upper surface of the horizontal, assuming it is coinciding with the slope face like this, you have your phi angle to be 0. And then it is saying the transition from one condition to another occurs when the tension crack. So the tension crack, which they said can either occur here or it can occur at the surface like this. These are some of the conditions that can result in plane failure analysis. Okay, coincides with the slope crest, and then you can have this expression 1 minus cot phi f and phi p tan phi p. So where z is the depth of the tension crack. So assuming a tension crack occurred from the top here, you need to know the depth of it, at what depth the tension crack is, and that will represent your Z. The phi P is the dip of the sliding plane, and then this F is the slope height. So if I happen to depict some H here, that becomes the H you see there. And then they have resolved some trigonometrics, and then they've come up with these angles. So let's have a look at this configuration. These were the angles I was showing in the other picture, and I asked us to identify. And so this is also the tension crack we are talking about. So I have a tension crack occurring here. So these were the conditions. That's for this type of failure to occur, which is a plane analysis. It's either the tension crack occurred at the top to result in the failure, or it occurred in the face of the slope. And in either case, if it occurred at the topmost parts of the slope face, these are some of the mathematical trigonometries we can do to come up with the various analysis that we can use in resolving our factor of safety, okay, resolving the causes of the failure. Then we also have this one, which is also resolved from this figure. And so based on the concept illustrated in this figure, so if I have this, so if I want to explain this as we saw in the earlier pictures, the distance from this, which is this diagram, so you have this as phi s, which is the phi s they showed you here. Where is it? Sorry. This. So it said that when the upper surface is horizontal, you usually will have this phi s, which is this angle to be equal to 0. And that is what they are showing. But in this case, this surface here we are considering is not horizontal, and that is why you have an angle phi s there. And from that, the tension crack Z, which is the distance or the length of the tension crack or its depth, is also denoted as from this top to this other line here, and that is denoted as the Z, which we saw in the previous formula. Then again, you have the height of the slope, which is this H here. You have this U. Who can tell us what the U is? We have talked about that. That is the force as a result of the pore water pressure, the uplift force that is going to occur as a result of the pore water pressure within the formation. We denoted that in the previous slides. So that is the U. And this V here is the pressure that is being exerted, the force that is being exerted as a result of the tension crack, which has accommodated some water in it. And that is also denoted as the V.